Good evening. This is Professor David J. De Los Reyes. My topic for tonight will be identities, trigonometry. It seems I've been noticing on YouTube that there are some missing things. Okay, people are not fond of what they call this in the so-called derivation of formulas. Because just like in the so-called differential calculus, if you don't know how the derivative formulas or the differentiation formulas have been what you call this derived, okay, it's hard to memorize. But if you know how it was derived, there's no problem if you forget it. You just derive it. And one of the problems on identities, this is just for illustration. Because the popular identity in trigonometry, the most popular is actually sine square of theta plus cosine square of theta is equal to 1. Meaning, in any right triangle, if this is theta, okay, the sine of this angle, if you square it, and the cosine of this angle, if you square it, this sum should be equal to 1. That's it. Okay, so the problem for tonight is that we are to prove that the sine square of any angle theta plus the cosine square of that angle theta is equal to 1. Oh, this is just because the proper way to read this one is cosine square of theta, or it could be written as something like this, right? Or in its simplified form, we remove this quantity here. This is actually sine square of theta. Sine square of theta plus cosine square of theta equal to 1. We are to prove that the sine square of theta plus cosine square of theta is equal to 1. And the next problem is prove that there's another identity. Prove that 1 plus tangent square of theta is equal to secant square of theta. We are using this under the integration of trigonometric functions under integral calculus. Okay. One of the solution of the trigonometric integration, the power of trigonometric functions is actually using this relation here. 1 plus tangent square of theta equal to secant square of theta. But for tonight, this is just trigonometry identities. We'll try to bring out the proof of this. Okay, let's try to bring out the solution. To bring out the solution, draw a right triangle. It's always like that. In trigonometry, it's always the basic thing is actually to draw a right triangle. Okay, so this is a right triangle in which the opposite side is y and the adjacent side is x, and the included angle here is theta. I will designate this as theta, so I will follow this. Okay, and I will place the hypotenuse to be the length of it to be 1 unit. 1 unit. Okay, so from this right triangle here, we could derive the relation of x in terms of theta and the relation of y in terms of theta. Okay, by definition, the sine of this angle here is actually opposite over hypotenuse. Right? That's the definition of sine. For any right triangle, it should be opposite over hypotenuse considering this angle, because considering this angle, this is opposite. Considering this angle here, this is adjacent. So if we try to take the sine of theta here, it should be y over 1 unit, or this is simply y over 1. Y over 1 is just y. Therefore, sine of theta is equal to y. That is the opposite side as a function of theta. Okay? That is y as a function of theta. Okay? The second one, take the cosine of this angle here. Cosine of this angle here is adjacent over hypotenuse. Cosine of theta will be x over 1. X, this is 1 unit, so this should be x over 1, or just simply x. Therefore, cosine of theta is equal to x. So we are now given x as a function of theta. Okay? We derive the relation using the so-called definition of sine and cosine based on a right triangle. The basis is always a right triangle, right? And using the Pythagorean theorem, okay, uh, the square of the hypotenuse should be equal to the square of the adjacent side plus the square of the opposite side. Hypotenuse square should be adjacent side quantity square plus the square of the opposite side. The hypotenuse is actually 1 unit, so this should be 1 quantity square equal to, the adjacent side is x, so this is x quantity square. The opposite side is y, so this is plus y quantity square. But we now know the value of x as a function of theta and the value of y also as a function of theta. So actually, we will replace this value x and y by h equivalent. We derive it already. Y is actually sine of theta and x is cosine of theta. So following this formula again, 1 should be equal to cosine of theta quantity square plus sine of theta quantity square. Squaring the right hand side and rearranging, sine of theta quantity square is actually sine square of theta. Cosine of theta quantity square is cosine square of theta. I just rearrange and they should be equal to 1. That's it. So we have proven that sine square of theta plus cosine square of theta equal to 1. And to derive the second identity, we are using this under integration of trigonometric functions. Okay? Under my course, Integral Calculus, it seems viewers like this solution over here, secant square of theta. Okay? So from this derived relation sine square theta plus cosine square theta equal to 1, we divide both sides by cosine square of theta. So sine square of theta over cosine square of theta plus cosine square of theta over cosine square of theta. We divide all terms by cosine square of theta equal to 1 over cosine square of theta. This is 2, this is 2. So actually we could factor out the power 2. So it can be written as simply sine of theta over cosine of theta all quantity square. It's the same. I just factor out, right? Cosine square, this will become 1. Right? Anything divided by itself is equal to 1 except 0. Okay? And the right hand side, this will become 1 over cosine square of theta. Okay? But under the definition of the trigonometric function, sine of theta over cosine of theta is actually tangent of theta. So we will replace the sine of theta over cosine of theta by tangent of theta, all quantity square, plus 1 equal to. And also by definition, 1 over cosine of theta is actually the reciprocal of cosine is actually secant theta. Okay, you could square this one if you want. So meaning 1 over cosine square of theta can be written as secant square of theta. So the right hand side now is secant square of theta. Rearranging the left hand side, 1 plus tangent square of theta equal to secant square of theta. So this identity is actually this. So that's the derivation of the relation of sine square theta, cosine square, and tangent and secant square. These are the ones we are using under integral calculus under the so-called evaluation of the integration if the given functions involve powers of trigonometric functions. That's it, guys. What I just presented tonight is derivation because it seems as I was watching videos on YouTube, they are not fond of what do you call this derivation. They go directly to the problem. Oh, but that's their choice, right? But for me, for you guys to learn more, you should try to derive your formulas if you can. Because if you can, okay, if you are in the field and you don't have anything with you, you could derive it. Okay, good evening, Los Angeles.